All right, so we were talking about chapter 9 here, I think, and we talked about a few things in chapter 9. One of the main things we talked about was the idea of intermolecular forces, I believe. And again, in terms of that, intermolecular forces, these are again the forces that hold two molecules together. And they're all pretty much, as we talked about, really based off of a pretty simple idea of basically opposites attract. So the positive side of one is attracted to the negative side of another. And there's really kind of three big classes of intermolecular forces. There are hydrogen bonding. There's dipole, really. And there is dispersion forces. And hydrogen bonding is typically what we find for polar molecules that has a hydrogen that's bonded to a nitrogen, oxygen, or fluorine. And because it's bonded to a nitrogen, oxygen, or fluorine, it's going to create a pretty polar bond. And it's going to really allow sort of that positive negative attraction to sort of happen at that bond, like what we see in water, that OH sort of group there. Oxygen being more negative, hydrogen being more positive. So it allows that hydrogen bonding to do its thing. As we talked about, not everybody that has a hydrogen, right, has the ability to hydrogen bond. So it really does need to sort of be that hydrogen that's sort of directly attached to one of those three elements in order for really hydrogen bonding to take place. Dipole is the main force for also polar molecules. But really, these are the guys that sort of lack the hydrogen bonding ability there. So they will just sort of bond to each other through what's known as dipole. Underneath that, there's ion dipole and interaction that occurs as well. And that's how we talked about when ionic solids dissolve, say in something like water that's polar. Dispersion forces is really your kind of main force there for nonpolar molecules, and they are temporary and weak type forces that occur, and they really can occur in sort of two sort of fashions. One fashion is you got something that has a charge, like a polar molecule next to a nonpolar substance, or an ion next to a nonpolar substance. And what that will do is temporarily sort of create a charge in the nonpolar guy, and they'll have a way to sort of interact with one another. It's weak because as those things sort of move away, they were not able to sort of maintain that. More commonly, though, what happens a lot of times is what is sometimes referred to as an instantaneous dipole, and that's a result of the electrons in those nonpolar molecules just kind of moving from one side of the molecule to the next. They may all sort of migrate one way or the other, and that will also create sort of a temporary charge in that nonpolar molecule, which allows it to interact with another nonpolar molecule via the same way. So out of the strength of all these, that's really your kind of strongest guy. So anybody that can sort of hydrogen bond or multiple hydrogen bonds in a sort of molecule definitely will have things like a higher boiling point, melting point, because of that strong interaction. It takes a lot more energy to break them apart from each other to get them into the gas phase. That results in those higher sort of boiling points, sort of things that you see. Dispersion forces is definitely the weakest type of interaction that you can have, and usually results in very low sort of boiling points and melting points because of that. As we talked about, I think organic molecules, which are mainly carbons and hydrogens, are a lot of times will have very low sort of melting points and boiling points, and why they're in gas phase a lot easy, or go into the gas phase very easily, which means they're very volatile in that case. Dipole is a really strong attraction as well. Hydrogen bonding is a kind of special type of dipole sort of interaction, but it is sort of classified a lot of times as sort of by itself because of that strong interaction that occurs with it. We talked about a bunch of stuff, but we also talked about, I think, kind of phases is sort of where we were at. We're talking about kind of the differences in changing phases, going from, say, solid to liquid, liquid to gas. And you obviously could go from solid directly to gas and back. Remember, these are the changes of states that we've talked about. That's our melting, right? That is our freezing. That is our evaporation or our vaporization. That is condensation. That is sublimation. And that is deposition going this way. Now, in terms of energy, obviously, as we go this way, it is all kind of endothermic processes. Heat and energy needs to be put in to do those processes. And as we head the other way, exothermic type of process where heat and energy has to be released. We talked about a little bit in terms of energy, that there is actually a certain amount of energy required to do the phase change. And when you change the phase of a substance, it does happen at the same temperature. So for example, the normal melting point or freezing point is where a substance will change from solid to liquid. Normal boiling point is where it will change from liquid to gas and backwards. And that change does occur exactly at that temperature. So again, for something like water at 100 degrees Celsius, you have actually both phases sort of happening at the same time. And also for something like water at 0 degrees Celsius, you also have both phases happening at the same time. Not to get a little bit above those temperatures that you actually do sort of transition into the next phase. And the delta H of fusion, or the heat of fusion, is the energy required to basically do that transition from solid to liquid or liquid back to solid. The number is the same regardless of which way you're going. The sign is different depending if it's exothermic or endothermic. So obviously exothermic stuff, as we've been talking about, are usually negative type values in terms of energy. Endothermic values are usually positive sort of numbers. The delta H is sublimation, is what we use to go from liquid to gas and gas back to liquid. Once again, it is the same number regardless of which way that you go. There's a lot more energy required to do that transition of liquid to gas than there is from solid to liquid. So for something like water, it's about 333 joules per gram to go from solid to liquid. To go from liquid to gas is about 2,260 joules per gram. So a much larger amount of energy is required to do that transition of liquid to gas. And that is because you are basically separating everybody from each other into the gas phase where they are flying around. Any questions on any of that stuff there? So I think we kind of finished up looking at a heating cooling curve that I think I drew, but again, that is the idea. Again, these transitions is where we have our delta H of fusion, our delta H of vaporization in terms of energy. And I think we also touched upon it. Anywhere you look at this sort of graph like this, a heating or cooling curve, where it's kind of going upwards, if you will, they are in the same phase all the way through here, for example, but they are changing temperature. And something, again, we don't talk about in this class anymore, but you will in the next class, and maybe you talked about in your previous class. That is where you would, if you want to figure out the heat, use the specific heat equation for that. So the specific heat equation is used to calculate the energy when you are in the same phase but change temperature. Delta H of fusion or vaporization is used when you are changing states but not temperature. So temperature stays the same, change of states. Heat of fusion, heat of vaporization, changing temperature but not the states. Then you have your specific heat equation. All right, the next thing we're going to talk about then is actually, sort of the relationship between pressure and temperature that is necessary to sort of change phases. And these are sometimes represented as phase diagrams. And phase diagrams basically show the 3 phases and the 6 interconversions between them, and associated temperature pressure values as necessary. So when we talk about the 3 phases, that's our solid, liquid, and gas. When we talk about the 6 interconversions, that's what I just wrote there. That's the melting, the freezing, the boiling, the evaporation, the condensation, sublimation, and deposition. We'll see on there that there's a triple point where basically all 3 phases are happening at the same time. Water has an unusual melting point line, has a negative slope, and that's because we see that ice is less dense than liquid water. Let's take a look at one here, I think, or a couple other important parts of it. We will also see sort of on these graphs what is sometimes referred to as the critical temperature. The critical temperature is the temperature above where there's no real distinction between liquid and gas, basically, sort of where it kind of blends in above that particular temperature. There's also a pressure that goes with that, where there's basically a critical pressure where, again, there's kind of no distinction between that. It is also sometimes referred to as the critical point on the phase diagram. Above the critical point where you have the critical temperature and pressure, you basically got something that kind of flows like a gas, but has properties of a liquid. They kind of blend together. And that is usually where you find what is referred to as the supercritical fluid. And that has the density of a liquid, but really does kind of flow like a gas on that sort of graph. So here's a generic phase diagram, and here are the three phases, and usually this is how it looks: solid to the left, liquid in the middle, and gas on the right. These are our 6 interconversions. That is our melting, that is our freezing, our vaporization, condensation, sublimation, and deposition sort of happening there. And that is as they cross basically the line there as it goes from, say, solid to liquid or liquid to gas as well. This is down here, sublimation and deposition. It is going directly from solid into the gas phase, no liquid phase as you go through there. So this is the pressure and the temperature associated with that. And here's a couple other important points. Right there's the triple point. That triple point is where all 3 phases basically are happening at the same time. So that would be your kind of pressure temperature combination to allow that to happen. And here's the critical point up here. That's where we find our critical temperature and pressure. And above basically those temperatures and pressures, we hit a supercritical fluid. It really kind of has liquid properties and it kind of flows into sort of the gas region there, and it will sort of flow like a gas. So this is what a generic sort of phase diagram looks like. That is your melting point curve here, where we have our transition between solid and liquid, and our vapor pressure curve or boiling point curve kind of going this way, obviously, as we are between those two. So if we look at one, for example, here of carbon dioxide is dry ice. And as we know, hopefully, about those properties, dry ice pretty much goes from solid directly to gas, right, under normal conditions, skipping the whole liquid cleanup. And we can see why that happens in this particular case. Normal pressures is around 1 atmosphere, right about there, which means under normal pressures and temperature, which is like 25-ish degrees, I went pretty much straight across there-ish, went down a little bit, but went straight across. I did not hit liquid at all, right? So I basically crossed over from solid directly into gas, which is why dry ice does that. If I wanted to force dry ice to go into the liquid phase, I would need to get it to a pressure above this, right? So I would need to get a pressure at least above 5 atmospheres, about 5 times our normal pressure, and maybe a little bit more to force it over here. And I'd also need to get it above a temperature of like minus 56.6 degrees, right, to get it into the liquid phase. So that is why under normal conditions, right, we see dry ice just go from solid directly to gas, skipping the liquid as we do that. If I wanted all 3 phases to happen at the same time, I would need to get the pressure up to 5.1, right? And then also a temperature of minus 56.6, and we would have all 3 phases happening there at once. Over here is where this line sort of ends. Again, that is our critical point. So above that, we would find obviously a supercritical fluid sort of happening above that sort of temperature and pressure. So phase diagrams are used to help you determine what pressure or temperature combination you might need to get a particular substance, obviously, into a particular phase. Normal standard conditions, right, is 1 atmosphere, right, and a temperature of about 25 degrees. So that when we talk about where the normal boiling point and melting point would be for a substance, those are kind of the pressure temperature combinations that we would want to look at. And we would want to look at, say, the line, right, and see where that sort of happens. In this particular case, it never happens, obviously, as we guys basically just jump right over. But for other substances, that is what we would sort of be looking at 1 atmosphere, basically. If you wanted to figure out where the normal pressure and boiling point would be, or boiling point and melting point would be, you would go across your graph at 1 atmosphere until you hit those lines, basically, and that would tell you where your melting point temperature would be and your boiling point temperature would be. Any questions on that? All right, so why don't you try that for each of these combinations here for our CO2? What type of phases are we expecting to see here? Look here, so we got our phase diagram here. So we're gonna go 20 degrees and 72.9. So obviously we have a 72.9 line right there at the top. 30 is about there. So if we move back from 30 a little bit where 20 would be, that means our little point there lands in the liquid condition there. At minus 56.7, we actually do have a line there, and 5.1 atmospheres. That's going to put us right there, yeah. And that means that is the triple point. So we actually should have all 3 phases basically happening at once here. That's going to mean solid, liquid, and gas basically occurring. Questions on that one there? Going to 10 degrees Celsius and 1 atmosphere. So 1 atmosphere is here coming across at 10 degrees Celsius. I don't know, maybe about here or so, and that would be not labeled here, but that is our gas sort of region underneath there. So that would be gas. Minus 78.5, looks like it's back here, and 1 atmosphere puts us right there on the line, yeah. So that puts us on this line between solid and gas. And if you are on the line, that means you're basically changing phases and you have both phases in equilibrium with each other, which means we should have both phases basically happening. So if you do find yourself again on that line or any of those lines, you basically have both phases happening. It's that sort of change of phases occurring. And again, you would have both of them happening. 50 and 80. So 50 is way past 30, I imagine, and 80 is above 72.9. So that would put you, over here, and then we're above the critical point, which is right here, and that would mean that we have a supercritical fluid. So basically happening at that point, which means it's got properties basically of a liquid, but flows kind of like a gas. Any questions on how to read a phase diagram? So again, like I mentioned, if you have a question where it's like, what is the normal boiling point, melting point? Usually you'd want to find 1 atmosphere, go across and see where it crosses those lines. And then you could come down to the temperatures at what that would be. Yeah. Any questions on phase diagrams? Okay. All right, so this is a skate blade, nicely drawn, I suppose. But as we talked about a little bit about water here, water molecules, again, at the surface, if you ever skated or saw ice, right, it gets kind of liquidy, allows it to glide over it. We have the stronger ice underneath, which has all of these open spaces between the water molecules, which is why, again, as we talked about, ice has a lower density in the solid form than in the liquid form because of those big volumes gaps, if you will, between the different water molecules as they come together when they do hydrogen bond. By the way, a reminder that density does change with temperature, as you saw hopefully when you looked up in the table, right? Depending on the temperature, density stuff does change. So we do see sort of the maximum or greatest sort of density with water about 4 degrees Celsius. And again, we have ice having a lower density than liquid water. So that is because water, again, is doing those hydrogen bonding that occurs. And again, they just can't get themselves, because of that strong sort of interaction, to really pack in tight. And again, that is a very uncommon sort of characteristics of a lot of substances. Usually in their solid phase, they're able to really pack it in there pretty tight to one another. But because it's a really strong interaction the water has through hydrogen bonding, it doesn't really allow them to do so, as we can see here, we talked about. Now, water molecules and ice, again, because of that sort of separation that occurs when water freezes, it expands, right? So if we ever threw a soda can or something like into the freezer just to kind of cool it off really quick, and you forgot about it and you come back, right? You look at the bottom of the can, right? Just like bulging out and stuff like that. That's because your water molecules, right, are expanding, right? And the can's only so big, right? So it's got to expand the can. Hopefully it doesn't pop. And again, it's that big space between everybody. So as we talked about, density is mass over volume. So by increasing the volume of the water molecules in their solid state, we do see a lower density value than they can in that more fluid state, where they're able to sort of really have enough energy to kind of move around each other a little bit more. And they actually are able to get in tighter to one another because of that. But when they lose a lot more energy, they no longer have that energy to really move them closer to one another, and they are basically sort of staying away from each other in the ice phase. So all phases of matter except have a few exceptions when it's heated and contracted. As I mentioned, liquid water below 4 degrees is bloated with ice crystals. So when it warms from 0 to 4 degrees, the volume starts to decrease, which means the density goes up, right? And the warmer water goes down. And that's really important for how water freezes in things like lakes and streams and all those kind of things, because water freezes from top down, right? And if it froze the other way around, there would be some really unhappy fish, I imagine, right? Because what happens basically is your warmer water starts to drop because it's more dense, right? Your colder water basically starts to rise, and the happy fishes are floating around there, like our friend here, Melvin. That's Melvin the fish, by the way. Might be a question, you never know. So that's Melvin the fish floating around, although he does look like he's in an ice cube. It was old cut and paste clip art. What are you gonna do? But what happens here, right, is again, the warmer water, which is 4 degrees or so, starts to sink because it's more dense. Colder water again starts to rise. And what happens when it gets to the top is it creates this sort of insulated layer of ice that's on the top, sometimes stronger than other times, right? Because you can sometimes fall through the ice, right? If it's not fully frozen up there up on top. But it allows obviously all the sea life there in the bottom to basically still be swimming around okay, because they're not frozen, unless you drill a hole in the ice and do a little fishing, which you would not do to Melvin, right? Or anything like that. But again, that is why obviously sea life there is okay, I guess, or lake life and stuff like that are okay when things start to freeze, because that warmer water actually does go to the bottom. The colder water goes to the top. All right, so now that we talked about liquids, we're going to talk a little bit about solids and some different types of solids and how solids sort of come together in obviously the solid phase there. Solids are rigid. In most cases, solids obviously pack into each other pretty tight to one another. There's not a lot of room for movement, which is why they are rigid. They sort of lack the energy to get around from one another. There's a couple of types of solids. There's crystalline solids, which are very ordered sort of arrangements of atoms and molecules and particles, like ionic substances. They are crystalline sort of solids. There's also amorphous solids, which exhibit very little long-range order, things like glass and organic polymers as well. Now, a crystal lattice is something that occurs and sort of a crystalline solid. And that's what we're going to kind of focus a lot on, or mostly on here, is this type of solids where we have a lot of long range order for how things come together. And again, these are how like ionic compounds come together, or positive and negative ions. When they come together in a solid phase, they do align each other in a very ordered arrangement to maximize the opposites attract and minimize those sort of repulsive forces that occur. So when you allow it to cool slowly, they will arrange themselves to maximize those attractive forces. This creates what is sometimes referred to as a crystal lattice. And part of that crystal lattice is what is sometimes referred to as a unit cell. And what a unit cell is, it's a piece of sort of the three-dimensional structure of a solid that you basically could take out and pretty much use it to recreate the entire solid. So there's that much sort of order and arrangement of how everybody comes together that you can just take a little sort of snippet of it and rearrange it. So for example, if we had like a solid that was something like this, and these circles represent obviously say something like the ions or molecules that are coming together. And if we wanted to pick a unit cell, it's really important sort of how the unit cells are typically sort of chosen. Now you might say to yourself, all right, well, I'll just kind of grab this guy here. If I were going to do a box here and go, okay, I got me a circle in my box there, which is the atom. And you may think that's a pretty good sort of unit cell. The problem with sort of picking a unit cell such as this is you don't really know how to put it back together. I got a circle. I'm not really sure how it lines up with somebody next to it, who on top of it, and that type of stuff. So typically when we choose a unit cell, we don't want to kind of just choose like one sort of atom or so in there. We want to choose something that has some type of relationship for how everybody else is together. So for example, if I chose my unit cell here like this, where I maybe grab a little bit of everybody or a little bit of four neighbors to each other, what that gives me is a unit cell that looks something like this. And now because I have some relationship of how everybody sort of comes together, I can now, if I build my squares, okay, I just need to kind of line up those guys. And if I pop a square up here, and I put another square over here, now you can see I'm really rebuilding my whole sort of three-dimensional sort of structure by really just popping that little unit cell or square back together. So oftentimes when we do choose these sort of unit cells, what we're looking for again is not just necessarily one entire sort of atom, but we want some relationship of neighbors and how they kind of sit together next to each other. And that allows for a much better sort of choice, as we can see here. So again, in this particular case, if we chose this as our unit cell, we got a little bit of relationships between the neighbors. We also see in this particular case, there's actually a whole cell or a whole atom sitting in the middle of those neighbors. So again, it gives us sort of that orientation of how things come together. Unit cells are usually three-dimensionals. They usually contain 2 or 3 layers of particles that happen. Again, with any type of unit cell, if you sort of choose it correctly, you can use it to, as you can see here, really rebuild the entire sort of three-dimensional structure of that solid, of how they come together. There's different types of unit cells. There's cubic, tetragonal, and so forth. We will be focusing in on really just basic cubic unit cells, where basically there's kind of 90 degrees happening in all sides. Also, because it's a cube, that means that something like volume is equal to length cubed, right? Like when we talked about our length times our width times our height, right? Gives us something like cubic centimeters, which is a volume. So with a cubic unit cell, we kind of use that relationship as well. If we take basically our length cubed, it will give us the volume of that particular cell, much like what we talked about with like density. So let's talk a little bit about these unit cells, and something we're not going to go into too much detail of, but the number of particles that basically come in contact with each other are referred to as the coordination number. So for ions, obviously opposite charged guys are going to come in contact with one another. The higher the coordination number, that means there's more interactions, and the stronger the attractive forces are. Because the higher coordination number, that means there's more things in contact with each other, which by default means they're attracted to each other, right? So they have to be in contact with each other. There's something that's referred to as packing efficiency. And again, we're not going to go too much detail on that, but it's basically the percentage of volume that is occupied by the unit cell. The higher the coordination number, usually the more efficiently that everybody's packed together. That's because if you just think about it logically, the only way to get a lot of contact right is everybody needs to be pretty close to one another, right? So if it wasn't really packed in very tight to one another, there wouldn't be a lot of contact with all the different atoms. We would have a lower coordination number rather than a higher coordination number in this case. And really what that sort of really refers to is something that we sort of talked about a little bit earlier, which is the idea that, you know, when things do come into the solid phase, they do sort of continue to sort of move around, right, to maximize those attractive forces and repulsion, minimize the repulsion forces. And that's sort of the packing efficiency there, right? They're going to kind of move around till they find the best sort of arrangement where they're going to be sort of happy. So we're going to look at, as I mentioned, really just cubic unit cells where we have 90 degrees in all corners. As I mentioned, if you take basically the length cube, that will give you the volume. We're not going to deal too much with the sphere, but the volume of the sphere is 4/3 pi r cubed. Now, there are a couple of things that are important in terms of how we count atoms. And when we do these type of things, it's important to know how many atoms you're dealing with. You know, is there like one atom in that unit cell, two atoms in that unit cell, or so forth. So when we have a cube, and not greatly drawn here, but when we have a cube, any sort of corner piece that has a piece of an atom is basically an eighth of an atom is in the corners. You could also have a cube that basically dissects an atom in half, and you have kind of like the atom kind of split right down the middle, and that would be like a half of atom sitting there on the face of a cube. And at the edge, we could have a fourth of a atom basically hanging out there as well. So when we add up all the little parts from these unit cells, that's how we get to the total number of atoms that are basically in these unit cells. So there's basically three types of unit cells that we're going to focus in on. Simple cubic is sometimes referred to as SC. Body-centered cubic, which is BCC, sometimes referred to. And face-centered cubic, which is sometimes referred to as FCC. Really, and we're going to look at each of these a little bit more detail in just a second here, but each of these basically have a total number of atoms basically associated with it. And you should know how many atoms go with each of these. So in a simple cubic, there's just one atom that you get total. In body-centered, you basically get two atoms total. And in face-centered, you get 4 total atoms. Now, to calculate the edge length, which is something that's important, you take 2 times r, which is the radius, if it's simple cubic. You take 4 times r divided by the square root of 3 for our body-centered. And this is really, I'll rewrite it this way. It is 2r square root of 2. Although it may look like the r's and their square root, it's actually not in that particular case. And that would be how you would calculate for a face-centered. Now you can see there's a lot more atoms involved here with face-centered, so you have a much higher coordination number because you're going to get a lot more atoms basically in contact with each other. Rather than simple cubic, which has just one atom, you have a much lower coordination number basically happening because of that in this particular case. We also see that the packing efficiency is much higher there in face-centered, again, because you got a lot more atoms basically in contact with each other, so they're going to be able to get in there pretty tight. So let's take a look at each of these now, a little bit more detail. First one is our simple cubic. So our simple cubic basically has an eighth of an atom in each of the corners. So in a cube, there's 8 corners, right? And there's an eighth of an atom in each corner. So when you add up all the corners there, you get one whole atom. So 8 corners times 1/8 of an atom in each corner gives you 1 atom total in our simple cubic. The edge length there is 2 times the radius. And the coordination number here is 6. So again, basically you get 6 contact points between those guys when they come together. Here's a little wedge of that there. And again, as they sort of come together in three-dimensional space, we get those contacts that happen. And again, that kind of eighth of an atom sort of happening at each of those sort of corner locations. The next type of unit cell is body-centered, and body-centered is where we have basically the eighth of an atom in each of the corners. So we got our one atom from all the corners here. And body-centered means that there is an entire atom sitting dead center in the cube. So a full atom, not cut in half or anything like that, but just basically sitting in the middle of the cube. And that would give us a full atom in the middle, basically an eighth of an atom on each of the corners, which gives us a grand total of 2 atoms that happen in body-centered because of that. And to calculate the edge length, it is this one. This guy looks like the R got disappeared there. So the length is 4r square root of 3 in this particular case. We get a little larger sort of coordination number of 8 in this case because of that full atom that's in the middle. We get a little bit more contact that can happen between sort of the opposite sides of the cube when it comes together. As you can see here, here's our guy in the middle and our different sort of contact points that basically happen. And we got our one whole atom stuck right there in the middle. And then each of these wedges adds up to the second atom that is present. The last one is a face-centered, which is FCC. And it has, much like the other ones, it has, again, our eighth of an atom in each of the corners here. So that's going to give us one whole atom. Now, in this particular case, face-centered means that there's basically an atom on the face of a cube. And basically, when you take the cube out, you slice it right in half, basically. So you get half an atom on each of the faces. So there are, 1, 2, 3, 4, 5, and 6 sort of faces, right, to a cube, right? Up, down, left, right, all around. And if you have 6 and you only get a half atom because each one's sliced in half, that gives you 3 more atoms, which gives you a grand total of 4 atoms per this type of unit cell. To calculate the edge length, I think our square root got out of place. So the square root, there we go, it goes there, is going to be 2 times r, which again is the radius, times the square root of 2. Questions on that? So those are the 3 that you'll be responsible for: simple cubic, face-centered, and body-centered. Again, the 2 things that is really important to allow you to do these calculations, which we're going to go through a couple calculations here in a second, is to know, again, how many atoms each one contains and basically how to calculate the length of the cell. And there it is. So it's a much better picture here. You can see the slice basically of an atom. Looks like, again, it's just sort of sliced right in half there as it comes out of the unit. All right, so let's take a look at one of these sort of things here and see, how we can use this information to help us calculate certain things. So a very common thing that we sometimes would want to calculate, for example, is the density, for example, of a substance. So if we wanted to calculate the density of aluminum as it crystallizes in a face-centered cubic cell, it has a radius of 143 picometers. So ultimately what we are looking for is the density in grams per cubic centimeter. So we're really looking for these 2 things. And this is going to be really a volume measurement. And obviously that is going to be a mass measurement. So a couple of important things that we come across when we look at this is actually the way it actually crystallizes. So face-centered basically means that it crystallizes, as we talked about here a second ago, right here. So face-centered means it crystallizes like this, which means the number of atoms we end up with is going to be 4 atoms in that unit cell. So that is one of the important pieces of information that you can get from that. Again, we got basically the 3 atoms on the faces and the one atom in the corners that happens. The other important thing is how we calculate the length of a cell, which, as we saw on that slide, is basically 2 times r times the square root of 2. So the first thing we're going to do is actually use the number of atoms to basically go from atoms to grams. So knowing how many atoms there are in that unit cell will allow us to go from atoms to grams. If I wanted to go from atoms to grams, the key word there is atoms, which means our good friend Avogadro needs to come into play, right? We could use Avogadro's number to go from atoms to moles, and then we could use the molar mass to go from moles to grams. So that's, again, why it's important to know how many atoms you got going on in these. So that's what we're going to do. We're going to take the atoms. We're going to use Avogadro's number to go 6.022 times 10 to the 23 atoms per mole of aluminum. And if I stop right there, I would be in moles, but I do want grams for the density. So we're going to use the molar mass of it, which is 2698 grams per mole of aluminum. And that will give me here 4 times 2698 divided by Avogadro's number using our exponent button gets me a grams of 1.792 times 10 to the minus 22 grams. So what I just did there is pretty much the top part of density. So I just basically figured out the grams part from how many atoms there is to basically go from atoms to grams. Any questions on that part? So what's left for me to figure out of this thing is actually the volume part, which is cubic centimeters. So we got a couple of things going on here that we want to think about. And at some point, you're going to need to do some conversions. The only thing that we have right here at this point is the radius, which is given to us in picometers. And we're going to use that radius, right, to figure out the length, because in this case is 2 times r times the square root of 2. Now, thinking forward at this point, the units that I want to end up with in terms of volume is not picometers, but I do want to end up in basically centimeters, right, or centimeters, cubic centimeters. So at some point you do have to do that conversion. So sometimes it's just maybe better to do it up front. You could do it later, but again, at some point you got to do that conversion. So what I'm going to do is first off, convert my radius, which is 143 picometers, basically into centimeters. And by doing that up front, when I do my calculation for volume and everything, I'm good to go. I'll have the right sort of unit at the end. Obviously you could do it a little bit later, but it might just be easier to do it up front. So I'm going to do 143 picometers. Pico is 10 to the minus 12 meters. So we'll do 1 picometer is 10 to the minus 12 meters. And I believe in 1 meter, there is 100 centimeters, right? So that's going to allow me to basically get it into really the right unit. Again, you could wait on this, but might as well just knock it out here up front. And that will get me a number. Looks like 1.43 times 10 to the minus 8, and these are going to be centimeters. Now, just to be clear, I really haven't calculated anything other than just change the units, right? So now that I have it sort of in centimeters, now I actually want to calculate the length. So I have the radius in centimeters. So the length here will equal 2 times r square root of 2, which means 2 times 1.43 times 10 to the minus 8 centimeters, square root of 2. And that gets me, find it on my calculator here. Looks like something, I think, of 4.04, we'll call it 5, times 10 to the minus 8 centimeters. Question on that conversion. And again, this is obviously also specific for this unit cell being face centered. So that is different for everything else. This is not the volume, right? So, but because this is a cube, the volume will equal the length cubed. So what I need to do is take this number basically and cube it. And that basically will give me like centimeters times centimeters times centimeters, right? It gives me the cubic centimeters that I need for my volume. That gives me 4.045 times 10 to the minus 8 centimeters cubed. So I got that somewhere here. Do a 3, maybe a 3. There we go. That's going to give me 6.617 times 10 to the minus 23. The units now will become cubic centimeters, which is a volume. So that's good. And that really is the bottom part of what I need for my density. Any questions on that there? All right, so to finish this up here, we're going to basically calculate the density. Let's steal this box right here. So our density here will be our grams that we calculated based on how many atoms there are, divided by our volume that we calculated based on it being face centered in the appropriate length, which is 6.617 times 10 to the minus 23 cubic centimeters. And that gives me a density of about 2.70 grams per cubic centimeter. A long way to go to get to that. Any questions on that calculation there? So we can use how these sort of guys come together in their solid phase, how they come together in their unit cell to figure out things like density. For example, if you have the density, you could also work backwards and figure out how many atoms there may be, what the radius may be, the length. You could kind of go backwards as well. Any questions on any of that there? All right, so why don't you try one here? Let's do rubidium there. Body centered. Radius of 247.5. And again, our picometer there. 10 to the minus 12 meters. Yeah, let's take a look. So same idea here. We're going to try to find the density in this particular problem. It is different in the sense of how it crystallizes or goes into its unit cell there. It's going to crystallize in a body-centered cubic, which means that that is the one where basically we got a whole atom sitting in the center, and then we also have the eighth of an atom on the corners. And the important part of that is that that's like 2 atoms you got going on in that situation. Because of the way it crystallizes, because it's not, again, face centered like the last one. This one obviously being body center. The other difference as well is how we calculate the length of it. It is different because it is body centered. We're looking at like a 4r square root of 3, I think, is our length in that particular case. So again, there are differences depending on how it crystallizes in terms of how you would go about the calculation. So with that being said, we're still going to kind of approach it the same way. We're going to use the atoms there to get to our grams part, and then obviously we'll use the length there, or the radius, which is given to us obviously to get to our volume part. So starting with our 2 atoms here, once again, we're going to use Avogadro's number to convert that into moles. And then we'll also use the molar mass there from the periodic table to convert it into grams, which is basically what we need for the top part of our density calculation. And looks like we will end up in this case with about 2.84, we'll call it. 2.84 We'll go one more. 38 times 10 to the minus 22 grams. So that is the top part that has been calculated. Bottom part is again going to come from our radius. And once again, I'm going to kind of do the conversion up front to get me into the right units. So that's going to be a 247.5 picometers. In a picometer, we got 10 to the minus 12 meters, and in a meter, there is 100 centimeters basically happening. All right, scribble, I suppose. All right, so 247.5 times 10 to the minus 12 times 100 in this case. Going to get us 2.475 times 10 to the minus 8 centimeters. Any questions so far? Now that I have in the right units, we're going to apply our length calculation here to get the length of an edge of basically of that unit cell. So our length would be 4 times r square root of 3. That would be 4 times 2.475 times 10 to the minus 8 centimeters divided by the square root of 3. And times that by 4, divide that by the square root of 3. And looks like 5.716 times 10 to the minus 8 centimeters. Once again, that is not our volume, but really just the length of an edge of the cell. To get the volume, again, basically like our length times width times height type of situation here, we're basically going to cube that number. And if we do that, they're going to get us a 1.867 times 10 to the minus 22. Again, since we cubed it, we are now at cubic centimeters, which is the volume part of the calculation that we need. Questions on that one there? All right, all that's left now is to pop those two numbers together. I got one little box here. I'm going to go with it. Bless you. Density would be our grams, which would be 2.838 times 10 to the minus 22 grams divided by our 1.867 times 10 to the minus 22 cubic centimeters. 2.838 divided by our volume. Looks like maybe a 1.520. Looks like maybe grams per cubic centimeter. Be our density there. Any questions on that calculation there? So although it seems like a lot going on, and there is a lot going on, it's really just kind of two conversions, converting atoms into grams to get to the density part, the grams part, and using that radius to get to basically the volume. Like I said, some variations on this would be obviously they give you density, kind of work backwards, figure out some other aspect of it, but you just would work backwards on it. Any questions on unit cells there? All right, so as I mentioned, we're not going to talk too much about. That's good. They got the same numbers, so that's always good. I'm going to talk about too much about how they pack together and sort of different sort of packing schemes, if you will. But ultimately, as I mentioned earlier, they really do want to sort of pack themselves in as sort of tight as possible, based on obviously the attract and repulsive forces that occur. And obviously, as we saw, the more atoms that you could get into a unit cell, obviously, the tighter you could pack it in, and you'll have a higher coordination number because of that. All right. And again, this is why it works really well for ionic sort of compounds. They have very, very long range ordered of how they come together. And that's sort of our sodium and chloride coming together, with obviously our sodium being smaller because it lost electrons, right? So it becomes overall smaller, like we talked about, chloride here becoming larger. Any questions on that there? All right, that wraps up chapter 9. We are off to chapter 10 now. All right, so the next chapter we're going to talk about is chapter 10. This will be the last chapter that will be on the next exam, which is coming up Monday. Yes, so we'll cover chapter 9 and chapter 10 coming up on Monday. We're going to talk about solutions in here. So we're going to talk a little bit more about solubility. We will also kind of review some concentration units that we did a little bit earlier on about like molarity, percent mass to mass. So we'll kind of go through those a little bit quicker than we did the first time. They should still be fresh since it is summer school and it was only like a couple of weeks ago, I think, or so. But unlike a normal semester, maybe it was a little bit longer. In the end, though, of this chapter, really what we'll be talking about and kind of using those concentrations and stuff like that is for colligative properties, things like boiling point elevation, freezing point depression, and talking about those type of things. But let's start with obviously solutions and liquids. So when we have two liquids that mix together, they are sometimes said to be miscible with one another. And if we have a couple of liquids that really don't mix together, they're said to be immiscible. It's sort of very similar to the idea of soluble and insoluble. So if something is miscible, it's soluble in each other. They basically mix together. And if something is immiscible, it's going to be insoluble in one another. So for example, ethanol and water are soluble in each other, are miscible in each other. And that is because ethanol, which is an organic guy, looks something like this. And water obviously looks something like this. And what we see in both of these guys is what we were just talking about. I got a hydrogen attached directly to an oxygen. Same deal here. We're going to get some hydrogen bonding occurring between these guys. The negative oxygen of one, positive of another. That allows them to interact really well with one another because they're basically using the same type of intermolecular forces. So if things come together that use really the same type of intermolecular force that something uses with itself, they're definitely going to be soluble in each other. And that's the case here with ethanol here and water. And if two liquids really are soluble in each other, when we look at it, say maybe in a test tube or something like that, it will all just look like one liquid, right? There won't be different layers or anything like that. Everything basically will mix together and you won't see those different layers. Now, different than that, if we take something like carbon tetrachloride and water, they are immiscible in each other. And that is because our friend water here is wanting to use hydrogen bonding. We draw quickly a quick Lewis structure without all the dots. You should hopefully recognize that as a symmetrical geometry, no dots on the central atom, everything attached is the same, which means this molecule is actually going to be nonpolar, right? And a nonpolar molecule, as we just talked about in the previous chapter, is going to want to use dispersion forces, right? Those really weak interactions, right? So you got water that definitely wants to use hydrogen bonding pretty much as its main route. You got carbon tetrachloride that wants to really use dispersion forces. You're going to get that like a little bit of mixture and then it's not going to be able to sustain it. What's going to happen here is you're going to get that polar induced dipole action that's going to happen with dispersion forces. And again, it may interact for a little bit, but over the long period of time, there's no way to maintain that interaction. And what you would see in that situation is a couple of different layers. Yes, so you would see one layer and another layer. So this brings up the idea that you very commonly hear when we talk about solubility in general, of the idea of like dissolves like. So things that use similar intermolecular forces should be soluble in each other. What that basically means is if you take something that is polar and polar, you're going to be good, it's going to be soluble. You take something that is ionic and polar, it will be soluble. If you take something that is nonpolar with something that is nonpolar, it will also be soluble. They both will be using dispersion forces, so they will be able to interact well with one another. It is only when you kind of cross over there, you take that polar guy and that nonpolar guy, it's going to be insoluble in each other because of the differences in their intermolecular forces and the way they're trying to interact with one another. That is why we say a lot of times water is a really good solvent, because a lot of times what we deal with is polar things and ionic things, which means water works very well for 2/3 of the majority of everything. Water is a terrible solvent for something that is nonpolar, and that's because they're not going to be able to interact well with each other. Hence something like this. Or if you took some iodine crystals, and you want to dissolve it in water. Not so good because I2 is nonpolar, right? So it's not going to dissolve in the water. But if you took that I2 and you threw it in something like hexane, which is basically all carbons and hydrogens, which is nonpolar as well, you're going to be good. You're going to get it to dissolve. Also, same thing if you took some potassium permanganate crystals. Try not to turn everything purple. We had the liquid version of that earlier, but take potassium permanganate, you're all good in water because that's going to be ionic and polar. It's all going to work really well. It's going to dissolve. But if you threw that guy into hexane, which is nonpolar, it will not dissolve. So again, that's why when we think about solvents, we want some type of solvent that can interact really well with our solute, which is the smaller part of a solution, to allow things to dissolve. Any questions on any of that? And that's what we see here again, some separation of the different liquids, because again, they have no way to maintain interaction with each other. Now, when we talk about solubility in water, definitely anything that's ionic is going to work really well because they are going to again be using the ion dipole interaction, where you've got the positive ion being surrounded by like water, for example. Again, the oxygen of water being more negative would surround the positive ion. The hydrogen of water being more positive would surround the negative ion. As we talked about before, that's basically how things are able to dissolve. All that water molecules come together. Now, we also have things like we just saw there with ethanol, for example, that are non-ionic, that are still soluble in water. And again, it is that presence of some type of group that allows it to interact well with water. So ethanol, as we saw, has that OH group on it, and it's able to hydrogen bond with water. Sugar, which is basically sucrose, is a little bit larger of a molecule, but it's pretty much surrounded everywhere with OH groups. So there's like OH groups everywhere on it, which means everywhere there's an OH group, it gives it a place to interact well with water, which allows it to be soluble in water, even though it's a little bit bigger of a molecule than, say, sugar. Now, solubility does decrease with the size, especially when you're dealing with something like an organic molecule like ethanol. Ethanol is really soluble in water, and that's only because it has really a couple of carbons, basically. It's not such a giant molecule. But if you would take something like this guy here, which is not ethanol, I'll tell you what it is in a second, as soon as I count how many carbons I randomly drew there. Let's see, I think it was 8. I think I went with. There you go. There we go. And put an OH group at the end of that. So 1, 2, 3, 4, 5, 6, 7, 8. That's like 1 octanol there, which is also an alcohol, also an organic guy. Also has this group here, which is polar. It is pretty much not going to be very soluble at all in water. And that's because the difference between this guy and the guy on the bottom is that's a much larger part that is non-polar versus this guy. So solubility pretty much drops to nothing once you get about 6 or more carbons that get attached in there, 5 or more carbons, depending on the situation. And that's because what happens is you have 2 things that are kind of working against you. In order for something to be soluble in water, you pretty much has to break apart the water and water interaction, right? And that's what's sometimes referred to as solvent-solvent interaction. Water and waters are all hydrogen bonding together. And you need to replace those water-water interactions with something that is very similar in size and way they can interact. So although it has a very, very small part on the bottom there that can interact with water, there's this really large part that's not going to fit very well with all the other water molecules. And this is what is sometimes referred to as steric hindrance, which means you got this really big thing in the way of that interaction that you need. So this really big part that's nonpolar, where the carbon and hydrogens are going to basically interact and interrupt that small little interaction point where water can kind of get in there. It's like trying to park a car into a garage. It works pretty well, right? If you take a big, truck, semi-truck or something like that, you can maybe get part of it in, but it's not going to really fit just right in that garage, right? And it's not going to interact really well. And it's the same idea. When things get really too big, it creates problems. And that, again, is because what we're really trying to do is replace, for example, with water, these water-water interactions or solvent-solvent interactions, something that's very similar. So as the size gets larger, we start to see a decrease in it. But a lot of organic guys, if they do have this OH group, which is what alcohols are, as long as they got like 4 or less carbons, they're fairly soluble. But as you start to increase the carbons part of it and hydrogens, which are nonpolar, the solubility really starts to decrease. Opposite of that as well, as you increase, and it can happen in organic molecules as well, as you increase the number of OH groups on something, it actually becomes more soluble as well, again, because there's more places for water to interact with it. So this is methanol, which is like ethanol, also a small molecule able to hydrogen bond through its OH group that is there. There's our ethanol. So water and oil, they obviously do not mix, and that's because pretty much oil is nothing more than a super long chain of carbons and hydrogens together. So it's a really long chain of carbons and hydrogens together, which pretty much all these guys are nonpolar. So again, oil is going to want to use dispersion forces. Water is going to want to use hydrogen bonding. That in combination are 2 different types of interactions, with the fact that oil is usually a very large molecule, is not going to make for a very good sort of mixture. We do sometimes see, as we talked about, a little bit of mixing that occurs, right, even with these things. And that is, again, because everybody can use some version of dispersion forces, but over a long period of time, they can't maintain it. So again, I think maybe the oil, vinegar, salad dressing is an example, right, over a period of time, things will kind of separate out from one another. So again, that idea of like dissolves like is really important, and sort of how things interact with one another also important.